Well, thank you everyone for coming. It's a pleasure to have Dr. Tyson Phillips with us here today. He's going to tell us how to find chicken McNuggets in data point clouds today using localization techniques and give us a brief introduction to his PhD topic. So, without further ado, I'll pass it over to Tyson.
Was the clap for him or was that a pre-clap for me? Because that wasn't a very big talk. I'll just start the recording. All right. You'll have to be a bit patient with me. It's been 2 years since I've given a lecture in person because we've been on screens. But what I want to talk about is the main thing that came out of my PhD. This was the best result, and it's the thing that I'm proudest of. It's my biggest contribution to the area, and I use it in projects every year. It's really versatile, so it's something that you might find a use for as well. You could even use it to find chicken nuggets, okay? So that's the theme of the talk is chicken nuggets. They'll appear again later. All right. So this is coming straight out of a journal paper that I published a couple of weeks ago. It's been on my to-do list for a few years, but it's going to be public access, and I can give you a copy of it if you want to have a read. The method is called maximum sum of evidence. So it's the maximum of a sum of something that I'm going to call evidence, and it is really a likelihood. But I'll do the maths for that in a bit. I think it's the best thing ever. That was put in there to annoy Ross, who's not here. Okay. So I'll show you what's the sort of mathematical underlining? It runs off an objective function and a searching heuristic. Who's done Metra 3100 in here? A good percentage of you? You all look familiar. Okay, so in that course, I tried to bring in pose estimation a little bit. You had to find the triangle that Tim lost. You'll remember that. He loses it every year. It always shows up in the same place every year. I should change it. But in that course, we taught you about an objective function based on error. You were trying to minimize the range error. And you didn't really have to do a searching. You just did like a brute force because you had to find that rotation. So I'll show you a bit about those. They're definitely main parts of this. And then we'll use it on all these problems, which are pose estimation problems, are where is it problems, that's what I call them. What is it problems is things like object classification, and where am I problems, that's sort of a cheap third point because it's really just the inverse of a where is it problem. Where am I relative to the thing that's fixed? It's the same as where's the thing that's fixed relative to me, just inverted. And of course we'll answer that age-old question that I think that's probably why most people are here today is can we classify McNuggets? And I'll show you where it beats the competing algorithms in the space, and it flogs them. All right. So here is a big chicken nugget. It is roughly 40 meters tall if you look at that scale. But for the purposes of this, it's 80 meters away from the sensor, and that sensor is a pretty crappy one. By the looks of it, it's got 6 range measurements. And that nugget is allowed to move forwards or backwards, closer or further away from the sensor, okay? That's the data that we've got of those 6 little green dots. Now, if we put it at 90 meters, you could measure the error as the distance between the data we've got and where they appear closest on the nugget, all right? And likewise, at 90 meters, you could measure the range error. So what's the range measurement I've got and what range measurement would I expect for a nugget at 90 meters? And that's what you did in the triangle assignment. And these are both pretty easy metrics because you can see here, if I sum that error, they both have 0 error at 80 meters. So they're both pretty indicative. They're both telling me the nugget's probably at 80 meters. We can minimize a little local minimum of error here, but really 80 meters is the global minimum. And you might use that with a search heuristic that's trying to minimize something like nel de meet or least squares or something. So that looks really great and really intuitive. It gets 0 error at the right answer, but they suck. I'm going to show you why they suck by just changing one of those measurements. So I'll keep 5 of them the same, but that third one, I'm going to mess it up. For whatever reason, a bird flew through the scene, or there was a bit of dirt or dust, or just the sensor failed itself. But now, with those 6 measurements, that's what those objective functions look like. That minimum error for both the point to model or the range error, they're no longer minimum at 80 metres. In fact, if I show you the best solution, the point to model says that the nugget should be at 60 metres. That's where we achieve, I did bring it in because I'm not very tall. That's where we achieve this minimum here, is a nugget at 60 metres. Likewise, the range error, well, in order to balance those 6 range errors, it's had to bring the nugget forward 3 metres, and that's just moved that minimum a little bit forward. But you see, neither of them get to 0 anymore. So neither of them are right. And the problem with this is, well, what people tend to do with cost metrics, because they're not as clever as we are, I was being pretty rude, but what they do is they'll say, okay, well, we'll just segment the data that is the nugget and we'll try and remove that Z3 measurement. But then you've got a chicken and egg situation, because in order to segment, you need to know where the nugget is. And in order to find the nugget, you need to get rid of the bad data. And you can see that circular loop that you've just created for yourself. So we want a solution where we don't have to segment, where we can just accept the data as is and find chicken nuggets. The solution I'm going to show you, we're trying to maximise rather than minimise error. So you'll see this ugly mass over here. I'll make that real easy in a second. You're going to be like, they gave you a PhD for that? They did. So for the perfect measurements that I showed, they all tell me that the nugget's at 80 metres. Really quite clear if I look at that plot. And for the other plot, where I screwed up one of those measurements, 5 of them are telling me the nugget's at 80 metres, and one of them's telling me the nugget's at 60 metres, but if you took the global maximum of that, you've still got the 80 metres. So we haven't lost the ability to find where the nugget is with this metric I'm going to show you. Okay. Now I don't like to do too much math. I normally do it by hand, but this is, like I said, it's really, really simple. Let's suppose that we've got a whole heap of hypotheses of where we think the nugget is. 1 metre, 2 metres, 3 metres, up to 100 metres. We had 100 of them. We'll say M is 100 hypotheses, and there they all are. Let's say we've got n range measurements, and in the previous example, there were 6, right? So you just got a list of ideas and a list of measurements. We want to find the hypothesis, the jth index of these hypotheses. We want to find Hj that maximises the probability of it being where the nugget is. The probability that nugget is at 80 metres should be the highest. Okay, so we're looking for that index into that. Pretty clear? Cool. Told you, it's like one more slide of maths. Now there's this thing called the law of total probability, which we can use to bring in the measurements. We can say that the conditional probability of this hypothesis given this measurement times the probability of that measurement itself. If I sum them all together, I'll get PHJ. You've all seen that before in stat 2201, 2202. I'm just going to throw that right in there. Replace that PHJ with that term there. Just total law of probability. There was this guy called Reverend Tom Bayes. You've heard of him? 1708, I think. It's like the oldest reference in my PhD. He was a God-fearing man, and he said, well, look, the probability of A given B is equal to the probability of B given A times probability of A divided by probability of B. You've seen it written like that. I can replace this guy, H given Z, with this term here. So we'll do that as well. And then you see these two probability of Z's. Well, they just cancel. Super simple, right? So now we see that the thing that maximises this, the J that maximises this, Hj, is going to be our most likely hypothesis of where the nugget is. And I've just put in 2 really simple stats equations into that. Okay, so we're all in agreement. That's the best hypothesis. Let's have a look at the probability of Hj. That was the thing we were trying to find before. It's found its way back in. Well, we can say, look, if we don't take any measurements into consideration, all hypotheses are equally likely. You got no prior, you got no information. So they're each 1 on M. There were M hypotheses, they're each uniformly likely 1 on M probability. This probability of Z given H, probability that I would get that measurement given that hypothesis, we can turn that into a likelihood function, F. I'll find you, there you are. You could integrate F over a really small delta Z, and you would get the probability if you integrated either side, plus or minus delta Z on 2. That turns into this. It's sort of approximation, but still nonetheless, probability is pretty much proportional to the likelihood times the width of that area that you integrated. Haven't lost anyone? If the answer is no, you've just understood my whole PhD. Okay? See, it's so easy. Go and do one. They'll call you a doctor. You won't ever use it yourself because it's weird. I'm going to put those two equations in there. So I'll put the one on M in, and I'll put our density, our measurement likelihood. We're going to start calling this a measurement likelihood. I'll put that in as well. And I'll bring the delta Z out the front, and I'll bring that one on M out the front. They're just scalars. In fact, given that we're trying to maximize that thing in the brackets, we can burn them out. You'll still get the same maximum if you took the scaling constants out the front. They're called normalization constants in probability. But this equation here, that's the most important thing. That's the end. That's the entire theoretical formulation. And it's the maximum sum of evidence. You see, maximum, sum, and we're going to call this term here evidence. So if I take all of my measurements from 1 to n, and I say, what is the likelihood of that measurement given this hypothesis? It's a measurement likelihood function. What's the likelihood that I would get Z equals 17 meters if my nugget was at 18 meters, sort of thing. Calculate that for each of my measurements, add them all up, find out where it gets maximized. And you've just found the pose of the nugget. All right, so let's have a look at how do we model a measurement likelihood function. I can model a hypothesis I should say that all of these problems you need to have an understanding of the geometry of the model that you're looking for. You can't say, go and find me a flim-flam if you don't know what a flim-flam is, right? I think that's a word from Rick and Morty. But here's a nugget, and I put it in some hypothesis. It's got some x, y in rotation that's n, or whatever degrees of freedom the hypothesis is. It could be scaling and could do all sorts of things to the geometry, but it's something that I can geometrically represent. This is the beam, we'll say beam I we'll say it's a LiDAR because radars are the worst. This is a LiDAR. LiDARs are the best. We all work in the near infrared space. What is the likelihood of getting this observation given this hypothesis? Well, if I was to raycast against that hypothesis, and I showed you how to do that in Metro 3100, I'd get this dot here. That's my measurement model. And I say, well, look, I don't get that measurement when I do this. And there's an error there, but you've told us don't use error. Well, let's accept that our sensor has some uncertainty about itself. And if you look at the manual for any LiDAR, you'll see 2 or 3 centimeters standard deviation. They accept that their sensor isn't perfect. There's going to be some uncertainty and hopefully zero bias. If we draw that standard deviation and we center it on the model, our raycast, well then this height here, made from the measurement, is the likelihood of that measurement, Zi, given the hypothesis. Just using the measurement's uncertainty model. Pretty simple? So easy, you're just summing Gaussians. That's the whole thing, and it works. I'm going to show you why it works. There's more complicated things we could do, though, before we get into that. Implementation-wise, you can draw a line right here, and if you've had enough maths for the day, you can tune out for the next slide or two. But we can do more complicated things. What if I was to say my sensor is registered to the world? Sensor registration says it's located somewhere in the world using this frame transform. And my hypotheses, rather than be relative to the sensor, they're also relative to the world as well. All right? What if I had some uncertainty in that sensor registration? Because it's hard to know. When I install LiDARs on big, like bulldozers and rope shovels and drag lines and all sorts of things, and I can't tell you within an inch where that sensor is, even with survey gear and all the best stuff in the world. So I've got, the bigger the machine, the bigger the uncertainty. Can't measure through the machine's walls to find its origin that doesn't exist. It's not like playing with a CAD model. So I've got some uncertainty, typically a few centimetres and maybe 10 to 20 milliradians on the XYZ roll picture of the sensor. If I was to perturb that frame transform, if I was to sample that, sample some errors, we'll say 10 millimetre errors on position, 10 milliradian errors on rotations. If I was to sample those for some noise, add them in, relocate the sensor, and then raycast again, I'd get all these little other measurements. Sometimes I might tilt the sensor down a little bit and it might actually start to intersect the nugget at the front. Other times it might intersect the nugget a little bit later or somewhere around here, right? So all of these little crosses, I think there's 100 of them. I've taken 100 samples of this uncertainty, repositioned it and raycast it again, and I've created this distribution here. It's bimodal. So you can see, if I was to get a measurement that occurred here, that would be supporting that hypothesis still a little bit, whereas in the previous question, it wasn't. If we got a measurement there, we'd say that's not possible. But now, because we've mapped some of the uncertainty of one of the other frame transforms, we can represent that uncertainty on the measurement likelihood function. Super easy? All right. So that's what we're trying to get the maximum of, and I've just shown you some really simple measurement uncertainty model. I said it was a Gaussian, there it is. Or the really complex one, which you could find, I'm not going to go into detail here, but probability density estimation typically comes from sampling techniques, typically comes from something called kernel density estimation, which itself is pretty similar. For each of those little crosses, I just plant what's called a kernel, which itself is a little Gaussian. I just plant one of them on each of them and then I add them up. And those little Gaussians, they're like little piles of dirt. And if you pile them up, they'll make that nice pretty curve there. And you've recovered your density likelihood function. And really, really interesting, the paper that I was reading on kernel density estimation and ways to find what's called the bandwidth, don't worry about it, ways to optimize this comes from UQ. The head of the maths department has produced the leading paper on this in the world. It's got like 5,000 references. Go have a look at it. Grotowski, I think is his name. But it was nice to get a UQ reference in this. All right. So you can say, all right, I'm just going to stick with that one. Implementation, that'll do too. This one, I put a little hat on it because it's kind of an estimate. It depends on how many samples you did. You'll never truly get it back, whereas this one is actually parametric. We've said it is a Gaussian with this standard distribution. All right. So I'll show you what that. I'll sort of show you a plot of that objective function over the workspace of the hypothesis, and we'll use this problem here. It's a robot arm. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9 measurements, and it can be articulated in 2 degrees of freedom, θ1 and θ2. That's where it actually was. That's the true pose of the robot. It's a joint space, θ1, θ2, and that's the data we get. If I was to go for every θ1, θ2 combination under the sun, and I was to evaluate, oh there it is right there, the sum of those measurement likelihoods, I put the robot in, say, this θ1, θ2 pose, I would get a height of 10, whatever the units are on this. It's a likelihood, sum of likelihoods. I'm not really sure. But if I did it everywhere, I would get this curve, this sort of surface. You can see down the very bottom here, if I put the robot at 90 degrees and 180 degrees in θ1, so what's that? It's all the way forwards, and it will go 0 degrees. So all the way forwards, it's not going to create any of that data, and you're going to get zero sum of evidence. If I put it in the right pose, I don't know what that actually is, it'll be in the paper. That's the maximum. That H star corresponds to that pose there. So you can see we're trying to find the maximum of that. However, it's pitted with all these local maximums. Pain, When you're trying to search for something analytically and it's got local maximums, really annoying. Because that one over here will say HA, like an alternate hypothesis. That's pretty convincing, and if you model it, you can see why. It matches up with 6 of those measurements, 6 out of 3. So it's got 2/3 as much evidence as the actual true pose of the arm. Really annoying that we've created this objective function that always tells the truth, but has so many half-truths in it. So it can be hard to search. And you guys have done Nelda-Mead sort of simplex methods before for searching mech? No? Well, Nelda-Mead is basically, I put a triangle and I move the vertices of each triangle. Whichever one's the worst, I move that, I flip it over. And then once they're all pretty good, I start to make it small. It's pretty simple searching heuristic, and it should land on the right answer. So what I've done here, that's a top view of this surface here. And there's the answer we're trying to find, H star. And there's that arsehole. That's what the A actually stands for. You're recording this, can't slip. If I seeded my Nelda-Mead searching heuristic in all of these places, the dark green ones, they converged on the right spot, and the light green ones, well, they all converged on the wrong one. They all found that local maximum. And the ones that are white, they didn't converge on either. They went somewhere else entirely. Don't know where. The ones down here, they probably didn't go anywhere because there's just a flat surface. How do you do a gradient ascent or a gradient descent on a flat surface? That's another really annoying feature, is all of this has 0 evidence, measurably 0. Well, a Gaussian's never really 0, but it's pretty hard to search. So what we do is what's called a particle filter, which is I go over the full space, θ1, θ2. I've casted here 49 hypotheses, and I've evaluated the colour of the green is how tall is that surface at that location. You see the dark green ones are over near H star, and there's a few medium green ones near HA, and you see the white useless ones up the top there in the corner where it was flat 0. If I take each of those hypotheses and we'll say, call them hypothesis 1, 2, 3, 4, 5, 6, all the way to hypothesis 49, and I list them out here, and I do a cumulative distribution function, CDF, of their values. Where this is steep will correspond to the hypotheses that were good, and where this is pretty flat will correspond to the hypotheses that were bad. That makes sense? So what we can do, if I want to cast another 49 hypotheses, I can uniformly sample this axis here from 0 to 1 and come across, and wherever I hit the curve, I drop down, and that is where I'm going to sample again. So where it's steep, where this curve is steep, you've got lots of resampling. I'm going to resample around them. There was some good stuff over there. Where it's flat, there's like 1 there, which is like right up there. There must have been a sample right up the top. So not really going to resample around these ones. There wasn't much there for me to find before, but I will do these areas again. And when we resample, we add just a little bit of noise so we're not checking the same thing. Because, what would be the point of that? So that's a particle filter in action, which is a bit of smart resampling. And there's that resampling there. I've got lots of resampling of hypotheses 10 to 20, and they probably correspond to these guys in here. None of these guys got resampled, and I just added a bit of noise. And you can see here, as we go from 0 to 50, it converges pretty quickly. If I just keep on doing that resampling technique, I'll evaluate how good these are with the CDF, and I'll resample again. Evaluate these, resample, evaluate. And every time I resample, I just reduce that bit of noise that I'm adding. So it's sort of forced to converge. Okay? That is it. This is it on an IBIS. This is a published journal paper. This is an academic paper. I'm so happy about it. In this, I'm finding the pose of that's a 2D shape, and that is where I estimated it to be on that data. Given the model, I said this was the best X, Y, and rotation. So 3 DOF problem for a 2D shape. I spent $30 on some CAD depot and bought the 3D IBIS. Didn't tell my fiance about that. But you can see here there's so many measurements, a couple, maybe 100 or so, and that's found the 6DOF pose of that 3D shape. So X, Y, Z, roll, pitch, yaw. We can find the shape. We can find where that is, because that's what our hypothesis is. It's a 6DOF hypothesis, and we got heaps of them. It doesn't have to be geometric. This is showing the pose of a robot arm, which is theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. There's 6 rotations in that KUKA robot. And I have worked out these are the rotations that make the geometry model best fit the data. So it's working there as well. The more hypotheses, the more degrees of freedom, the longer it takes to search. It's like a curse of dimensionality. You know, you've got to search everything again, but now with this extra degree of freedom, so many times. So I'm working on methods right now to speed it up. We're trying to put it on a rope shovel for Caterpillar. And they will need updates at like 10 hertz, 20 hertz, so we're finding ways to throw it on GPUs and things. Okay, this is, I think, why most of the bums are in the seats, is they wanted to find chicken nuggets. Okay, I found this article by Haley Peterson, and it was the worst article I've ever found, but it inspired me to write a journal paper. Okay, if you've ever eaten McDonald's chicken nuggets, they come in 4 shapes. If you've ever looked at them and go, I've seen that shape before, it's because that's it. They only come in 4 shapes. There's a press and it's got four geometries, and these are the actual official names. They have a legitimate name. They're called the boot, the ball, the bell, and the bone. And if you read through this steaming pile of, can't swear, you'll find the answer as to why there's only, it's total clickbait, right? Why McDonald's only come in 4 shapes? This is their literal answer, is 3 would have been too few and 5 would have been like wacky. Idiot. Shouldn't say that. But you can understand 3 would be not enough and 5 would be too much. They also reached out to understand the origin of the boot, the ball, the bell, and the bone, but they're waiting to hear back, and that was how the article finished, and it just left me on the edge of my seat. That was 7 years ago now, looking at that, and I don't think there's been an update, so I might email Haley. I'm the integrity officer for the school, and you need to reference your sources. I got that in there. It's been through the reviewers, and Haley Peterson is about to get her first academic citation on why McDonald's chicken nuggets come in only 4 shapes. None of the reviewers looked at my references. We'll see. Okay. I'm going to conduct a little experiment with you. I want you to tell me which chicken nugget shape out of the boot, the ball, the bell, the bone, I'll put it up in a sec, is responsible for making this point cloud. And I've redacted the actual answer. Okay, this is the question. The Slido poll reactivate. It must have been, there it is. 188810. And I will open this up in a way that you can not see everyone else's answers, so as not to be persuaded. But that's the point cloud. They're the chicken nugget shapes. I should make it clear, they can be translated and they can be rotated. X, Y, and theta. Otherwise, none of them would fit.
Tyson, we can see the answers on our...
Oh, that's okay. As long as you can't see the actual answer. Boot seems to be winning. Bone is catching up, although it has fallen back. The bell has taken second place. No one thinks the ball? Let's have a look at the ball. Where you at? Yeah, no, it's not the ball. Okay, so what seems to be the winning one? The boot. People are saying boot. Bell's not far behind. Which one's the boot? People are saying this one, or maybe bell. Bone is coming in third, and ball is still got no runs on the board. Okay. The next slide is going to show you the answer. I'm going to fit each of these geometries to that point cloud using the MSOE method that I've showed you. And these are the best fits I can get with those 4 shapes. It was, of course, the bone. Who guessed bone? You can answer true to the title of this talk. Everyone else can answer no, I cannot. Although if you can implement this method by the end of the week, you can claim yes and join those in the bone who don't need to do it because they can do it from visual inspections. All right, so you can see what was our most popular answer was the boot. Let's have a look at the boot. The boot is a pretty good fit, but it's not quite. I think when I made this problem up, I tried to find something that would make most people say the boot. Oh, the boot's over here. Yeah, so you all thought it was this little knob end here, but it wasn't. This is actually the best fit. All right. What is the sum of evidence on those 4 shapes? That's it there. The bone is the most evidenced geometry for that point cloud. It's got almost a quarter as much more evidence as those other 3 shapes. We can do the same thing on chess pieces. Pawn, rook, knight, bishop, queen, king. You all know what chess is. You're all mechatronics students. But here is a confusion matrix where I have put each of those geometry models against a point cloud made by one of the other ones. So on the left here, I'm showing my fit of a knight against, I believe it is the queen point cloud. And the diagonal here is showing you that the pawn was the best for the pawn, the rook was the best for the rook, the knight geometry was the best for the knight. I should read it this way. The knight geometry was the best for the knight point cloud, the bishop geometry was the best. King and queen, pretty similar, but still the diagonal is a little bit darker green. And that's similar because they're almost identical geometry, except for the little cross or the little dot on the top of the crown there. Like, they're 90% the same geometry, and so you will get a fair bit of evidence to support that queen fitting the king point cloud, or the king fitting the queen point cloud. But it still gets it right. It can still differentiate between which of those fits the point cloud, which was interesting. And you don't publish results that didn't work, so all you're going to see today is results that work. Okay. Localisation is where am I? So what I could do is I could take a scan of a wall. That's actually a bit of the quarry out near the Toowong Cemetery there. There's a little quarry, and I took a scan of the wall, and I estimated where was the scanner. So sort of inversely estimating the pose of where is the platform, or really you could have uncertainty in that, again with the registration, where is the platform relative to the wall? And you can model that uncertainty in the registration. So if this was on a vehicle, I could tell you where the vehicle was. I'll show you some videos at the end where I've actually done this on real data and real equipment. Okay. This is what I believe makes this method superior to everything else in its class. On the left here, I'm fitting a model of Queensland and a model of Australia using MSOE to a point cloud taken from, looks like somewhere near Papua New Guinea, Fiji, maybe a bit south of Fiji, Papua New Guinea. Anyway, he's taken that scan, and that is the pose, that's the centre of the world down there. I chose a different coordinate system. That's the pose of the Australia geometry, and that's the pose of the Queensland geometry. They both seem to fit that data pretty well. There's a method called Iterative Closest Point method, and it relies on scan matching based on error. So it's trying to minimize error. This is the difference between me over here trying to maximize evidence, and this one over here is trying to minimize error. It can fit the Australia model to the data just as well as me. We got probably the same answer to nanometers and nanoradians, right? But the Queensland model is wrong. And it's wrong because it's tried to fit, it didn't segment out these 3 measurements here on the Northern Territory, and there's one measurement down there in COVID Sydney. So it hasn't it's tried to fit this geometry model to all of the Australia point cloud, and its best fit to minimise the error was to bring it a little bit closer to these three. So you can see why it hasn't worked. Here is ICP, and this is like the leading technique for fitting geometry to point clouds. Here is a Stanford Dragon. It's a really popular geometry model that's used in these kinds of papers, and there's 1,500 measurements of it. And with those 1,500 measurements, I can fit the Stanford Dragon to it beautifully. It fits, right? Why wouldn't it? But when I introduce another 1,500 measurements of just random stuff, it's screwed up. It's got no chance of fitting it because it's trying to fit it to 3,000 measurements here. The 1,500 true dragon points and the 1,500 not dragon points. So I'll call that 50% clutter. When I throw MSOE at the same problem, it doesn't care. Those measurements here, which aren't the dragon, they will support a hypothesis. You can put the dragon in a pose that would make, say, that measurement there. I could put the dragon right up here and it would be like, yeah, this measurement makes sense, but these other 2,999 don't. So they're not, while they do support a hypothesis, they don't support the same hypothesis. The true hypothesis is supported by half of the data here. No other hypothesis will be supported by half of the data, if that makes sense. So it is possible to make them, but not all of them at the same time. 70% clutter still works. 90%, even 99%, he's still in there. I didn't put this figure in the paper because at that point it was just kind of showing off. But this is how many, if we go back and have a look at the size of this dragon, how long is he? He's about 200 mil long and maybe 100 mil wide and 15 centimeters tall. Here is the error. Once I've put the dragon where I think it is, this is how many millimeters of error is any part of that dragon. This is the worst part of the dragon is displaced by this many millimeters from where it actually is and where I think it is. And it's only a millimeter or two. In fact, the worst one, which occurred at 97% clutter, probably just because of the bias introduced in my random sampling of adding in rubbish, looks like that. And that's the error on the dragon from where it should be. The worst, right on his toe down here, is 2.5 millimeters in error from where it should be. The rest of it's still it's less than a millimeter, most of it. So you get the idea? That's a really good way for, you can say, oh, it's got this roll pitch yaw XYZ error, but that sometimes means nothing because you can have large errors in those parameters, but they can cancel each other out a little bit. So really, when you're looking at pose, the best way to describe an error is to put the object where it is and where you think it is and say how much is that geometry displaced at its worst. That's a really good way of sort of saying how good the fit is. And 97% looks just like that. So 2 millimeters of dragon error in that point cloud. Well, that one's even less actually. That one was 2 millimeters. All right. What about when the data from the sensor has really large uncertainty in it? What if I bought a really crappy $100 LiDAR and its measurements were like, yeah, we think it's this plus or minus 100 millimeters, right? So as long as the bias is zero, the uncertainty can be whatever it needs to be because we're modeling it. We're modeling the uncertainty in our measurement likelihood function. So the green bunny here is ICP fit. The white bunny here is me. Normally you would have the truth, but me is the truth. So you see the green bunny starts to rotate to fit the direction of the scan noise, where our scan is sort of getting stretched in this direction that it's scanning in. And 30 millimeters, there's 50 millimeters. My bunny's not even moving. In fact, he's got a couple of millimeters, maybe 5 millimeters of error there, 10 millimeters at worst. Whereas the other bunnies, he's got 100. And these errors here will be just to do with the bias. This is not a zero mean bias that I've sampled with. I reckon if I had been careful and sampled and made sure the bias in that sampling was zero, I would probably be down here at 0. Okay. So this is the talk. What I told you was evidence is way better than error. Error is misleading because you need to segment the data. Not all the data belongs to the model, and I've shown you why ICP sucks. I've shown it works on where is it, what is it, and where am I? And it doesn't require segmentation. And this is the biggest contribution of my PhD, so I thought I should put it in twice. You don't need to segment. There's not many other algorithms out there that can claim that. That is huge. In field robotics, where you've got scenes that have got constant state of flux and stuff is coming in and out of it and dust and all sorts of rubbish, not having to segment is a really powerful sort of feature. And I've shown that it can deal with inaccurate measurements with the bunny, inaccurate registration. We can model that. You could even model the intrinsic calibration of the LiDAR itself. The manufacturer says the beams are pointing in this direction. Maybe they're not. Maybe there's some uncertainty there. You could model that too. Just sample it. That's the end of my talk. But I spoke for way more than Josh, and he got a clap. I don't want to clap. I just thought I'd show it working. So I think I showed this during the lecture. This was the original video during my PhD era. My MATLAB skills have gotten a little bit better since then. That is me estimating the pose of this dipper in crowd, which is the arm can move forwards and in. Hoist, which is the amount of rope that's spooled out. And the door angle, because I found the door angle was taking me to the wrong place. And that's it, actually loading a haul truck. So I'm estimating the pose of this. It gets a little bit lost down here when you don't get much data on the door. It opens up a little bit, and up at the top as well, it opens up a little bit because there's just no data on it. The LiDAR was put here to find haul trucks, not to find dippers, and I looked at the data and said we could probably find dippers with that, so it really wasn't located for this problem, and we would do a little bit differently. We're actually doing it now on another project. This is a P&H shovel. We're now doing it on Caterpillar shovels. Okay. This is the localization. This is on an underground mine. It's actually on the surface. It's a giant hedge maze down in Tasmania, a place called Burnie. There's a really good distillery right across the road. It's the only thing in Burnie. This is me driving, someone else was driving around this test track, and the yellow LHD that you see is where I think it is, and the green LHD that you see is where it actually is. And you can't see that because we're the same. It's underneath, but we've got a GPS solution there. So you see as it drives around, it's got a 2D LiDAR on the front giving the red data and a 2D LiDAR on the back giving the blue data. And we're able to estimate where the LHD is from each scan for the whole duration. He drives around a lot more, you don't need to see all that. But, okay. What else have I got? The robot project that I showed in Metro 3100 in the first lecture, some of you haven't seen it yet, but you will. This was this one. There's a Velodyne VLP16 on the end of this robot. That's why I had the cool robot geometry model for the paper. Came from this. And it's just taken a scan, and now it knows where that is, and it can go pick it up with deadly accuracy. And these are like 1-ton bombs, right? They're 700 kilo bombs, but they're filled with compressed natural gas. Okay. This is. I didn't show this in the lecture. I think I've got the underlying visualizer. Oh, this is from the days at Logan. This is like Inception because there's a video within a simulation within the actual thing behind it. This is the triple robot video. But this is using the same thing to locate where to put this cassette. Where was it? Where's it got to go? It's finding those geometries using exactly what I just showed you. So you could go and do this now. I think I zoomed. There it is. That was the best project. We got it to work in a giant workshop with a styrofoam haul truck. But the one I wanted to show was maybe this one. This is the animation. So this is what it did at the start. It went, give me a scan, please. There's the LiDAR data. It took a scan there, and it took a scan there, and it says that's where it is. Found it. Just before that pops in, the yellow is, I'm not a good surveyor. I'll tell you that. I've surveyed where I think the truck is, the cradle is, that shape. I've surveyed that, and this is what I believe to be the truth. Roll pitch your XYZ of that cradle. The green one that pops up on top of it is my estimate. So watch it do it again. So there's like the anatomy of a bee between those two origins. You don't use that saying that much. I made it PG. Okay. What else have I got? This was also from my PhD. This was when the no need to segment part really made itself clear. We've got this point cloud around the shovel. There's a haul truck there. And I'm trying to find where I think that tray is. You can see it clear as day, but it's really hard for an algorithm to find that because we've got all this other data here, especially when you've just dropped 100 tons of dirt in the back and it looks like this. Okay, so this is just showing it for a couple of swings of the shovel that we can always find the haul truck no matter where it is, no matter what it's got in the back. Those magnificent rainbow colours are all my hypotheses. The particle filter that I showed you, and that's them converging to a single pose. And that's that's the sum of the evidence here. You see it gets larger and larger. So that has 200 tons of dirt in the back of it by the end. And I think that is all of the videos that relate to this talk. I can dig up my PhD and show you a bit more of the truck tray. I've still got time. So we can find the dipper when it's isolated, when it's halfway through the dig face, when it's open, when it's dropping material all over the place. We can, that's the entire algorithm I just went through. That's the measurement uncertainty model. That's adding the door angle in. There's a truck tray. We can find it when it's empty, when it's got one load in, when it's got two loads in, and when it's got an entire excavated dipper inside of it. We can still find it. And the reason we can still find it is when it's empty, these are the points contributing evidence to that hypothesis. When it's got something in the back of it, sure, we lose all that evidence, but look at all this stuff on the front, still lights up like a Christmas tree, still supports this is where I think the truck is, and that's what we're leveraging to find it, even though we don't have that anymore. I think this headboard had like 20 years of damage, so it doesn't actually look like the original geometry anymore, which was interesting. Trying to talk to the figures. This is, we said, look, we can, when there is no truck, it'll still find a truck. It put the truck halfway through the dig face because there wasn't one there. So you need something to say that there's no truck there. It's not in the scene. And that was the final conclusion. I remember I wrote, the MSOE estimator always finds a truck. The MSOE estimator always finds a truck, even if there's not one there. And the MSOE estimator always finds a truck. So if there's two there, you won't get them both, right? And the reviewers came back and they said, you've put the same thing 3 times. And we wrote back, yes. That was a bit of fun. Anyway, that's it. Now you all know how to do your own variable stuff. You guys have any questions? I can show you the paper or other things. Yeah.
You mentioned that it always finds a truck.
what do you do if there's no truck and you want to it's running automatically, it doesn't know, you're trying to be elsewhere doing something else. How do you tell it, okay,
Sure.
Stop finding a truck now? Do you have two things communicating or?
Oh, I'll show you. Remember we said it's the sum of evidence is our guiding function. There was a plot, I should have spoken to it just then. I think it's the final figure. I'll show you what that sum of evidence looks like as we are filling up the truck and one comes into scene and one disappears. So we're estimating all the time, like you said. Go scroll up a bit. Really good question. See this? This is about 100 seconds of estimations, 1 per second. And in this, where it's this colour here, there's no truck in the scene, really low evidence. Then the truck, the shovel starts swinging and the truck pops up in the scene. It's changed its field of view. Oh, there's a truck here now. And the evidence goes up instantly. And the shovel's doing a dig, the truck's sitting there still. It's getting a really good estimate of where it thinks the truck is, really high evidence. Shovel swings towards it. The data might have a bit of skew in it because it's moving LiDAR. So it goes down a tiny bit. And we load the truck up. You put the dipper in, you've just lost a heap of evidence because you can't see the back of the truck tray. You've got stuff in the way. But it's still pretty high. You come back for that second swing and it's lower than it was originally because there's 100 tons of stuff in the back. So what we would do is have some sort of threshold. I hate thresholds in algorithms, but in this case, I don't have a better way to do it. That's the null hypothesis, is that there is no truck. And most null hypotheses are tested with a threshold. So we could say, look, if we ever see less than this is in standard operation. If we ever see less than this, there's no truck.
Okay.
But yeah, no, that's a really good question. This was the error. So there's my truck error. Yeah, a couple of 100 mil. And then the truck disappears, boom, 60 meters straight away. Yeah. Any others?
Are there any drawbacks with this method?
It's a bit slow. You can, though, because you can test hypotheses, the result, how likely is this hypothesis, doesn't affect how likely is that hypothesis. So we've thrown it on CUDA and had NVIDIA CUDAs, the GPUs, and had 3,000 cores trialing 3,000 hypotheses at the same time. And you could cook an egg on it. It shouldn't be a feature. I should put it in the slides. You could cook an egg on me. I run hot. That got us down to maybe a second or two for a 6 degree of freedom pose estimate, the one that you saw. You saw that got it pretty quick. But you can subsample the data to make it faster. You can have less hypotheses to make it faster. It seems to be linear with number of measurements and number of hypotheses. So if you subsample them and have a smarter searching heuristic that doesn't need as much data or as many hypotheses, you get there faster. Or you can get there more aggressively by reducing the noise and doing less iterations, trying to force it to converge quicker. But then if you try to make it converge quicker, you run the risk of landing on a local maximum. So you tend to go slower. It's a bit of a trade-off, as is all. But yeah, no, that's good. There's no real problems with it. It's kind of the best thing ever, as you saw. Yeah.
Are there any geometries that this doesn't work for, or that?
If you've got an understanding of it, you can find it. If you had a sphere, and I asked you to tell me what is the XYZ location of the sphere, that would be easy. But if I asked you to tell me what's the orientation of the sphere, you couldn't tell me, right? Because changing the hypothesis doesn't change the measurement likelihood. The sphere looks the same in any rotation, so that's a good question. The same thing goes for localization. If you're trying to find where you are, imagine you're in an infinite hallway. How do you tell how far down the hallway you are? There's no geometry to help you locate yourself. You'd just be running for forever and go, oh, I thought I'd been here before. Driving around a constant radius circle, if you're in a wall, same as the sphere problem. I don't know where I am in the circle. I could be anywhere in the circle. Yeah, but yeah, the geometry definitely plays in. Just on that sphere topic, some guys at Tarong Power Station up near Kilcoy, I think, they contacted us about a potential gig, which is they put these cement spheres in their milling machine where the coal gets sort of ground, and the spheres, they start off with 10 spheres, and the spheres are 800 millimeter diameter, and over time they shrink to 700 millimeter spheres, and then they throw in an 11th one just to sort of fill the void, like a cavity sort of thing. And they've got a guy who goes in and he measures the size of the spheres, and it's a two-man job because you need a spotter and it's a confined space, and he goes in white and he comes out black, and it's a disgusting job. I've seen him do it. And he measures the spheres, and he measures all 11 or 10 spheres to work out, do we need to replace these now with, go back to 10 new spheres, or is it time to put in the 11th one? He measures them all, and then he goes to the next machine, and they shut that one down for a month. And then he goes to the next machine, and they shut that. So that's his job, is to jump in there. We said, why don't we just stick a LiDAR down and we'll tell you how big the spheres are. We'll tell you where they are and how big they are. So our hypothesis there would be X, Y, Z of the sphere and radius. So the scale, we can actually scale the geometry as part of the hypothesis and test for that. So you got me talking about spheres. That's your fault. Yeah, well, we know where they should roughly be. That'll help seed us. But where they actually are, you need to know where they are to know how big they are. So it's all part of it's all coupled. Where is it and how big is it? You need to know one to get the other. Where's the origin to know how big it is? How big is it till I found the origin? So you put it in the hypothesis together. Oh, that's good. These are good questions. These are holes that I didn't realise I had in my talk. I'll fix them for next time. Awesome. That's all my IP. I'm useless now because now you guys all know this.